not only in our field of stem cell transplantation and autoimmune disease, but they're international leaders also in their specialties of neurology, gastroenterology, and Jan Storek is an international leader in haematology with an interest in scleroderma, who's here today to step in for Keith Sullivan, who unfortunately couldn't make it for various reasons. But okay, so we'll start with the first speaker, who really needs no introduction to us as EBMT members, because he's been so active in the EBMT, and it's Professor Paolo Muraro from Imperial College, who's I think really led the field in immune reconstitution studies, particularly in MS. Thank you, Paolo.
Thank you, John, for the kind introduction. So, the topic is as stated. This is really a simple question. How does AHSCT work, not only in MS, but in all of autoimmune diseases? And I'm going to tell you in about 25 minutes how all that works, of course. And so if you just pay attention, you'll leave and you'll know, you will have figured all out. Of course, I will, in reality, highlight, these are my disclosures, highlight areas of knowledge and as well as areas of uncertainties. And there are many areas of uncertainties, but I think all in all, the field has been successful over the past 15 years or so in advancing the knowledge of the understanding of mechanism of AHSCT for treatment of autoimmune disease. So, tackling off the first point of my outline, I'll just give a sense of MS pathophysiology to sort of lay the ground for the future, for subsequent discussion. And I'm not going to be able to do these for all of autoimmune diseases, partly because of my more limited knowledge of other autoimmune diseases, partly because it will require essentially all the time of the lecture. So I'll just use MS as an example, and I will probably show a majority of data of MS, immune reconstitution. So MS, unlike the other major autoimmune diseases that are considered potential indications for transplant, it is slightly different in that it is a good example of an organ-specific autoimmune disease. So, unlike SLE and systemic sclerosis that are more systemic, in MS, the target organ is confined to the central nervous system, where it produces lesions which are primarily inflammation-driven. So inflammation is key with blood-derived immune cells infiltrating around blood vessels and along the meninges, which leads to parenchymal central nervous system demyelination in the white and in the gray matter that ultimately results in injury to axons and loss of neurons, which is the correlate to the long-standing and irreversible neurological disability. Hence, how do we counter this inflammation? How do we treat it? Firstly, do we know how this inflammation arises? The problem is no, we actually don't know how the inflammation itself arises. There are two models which have been proposed to explain this. It could be that inflammation initiates as an immune response to antigens that are derived from the central nervous system and that drain to the cervical lymph nodes, where they activate T cells that drive T cell and B cell immune responses, which then involves homing of the effector cells to the central nervous system and the downstream inflammatory damage. But it is also possible that CNS inflammation may actually start altogether in the peripheral immune system. So I lost the pointer here. Okay, it's back. the whole inflammation process may be initiated in the periphery from peripheral tissue-derived antigens, which bear similarities to CNS antigens, and by way of so-called molecular mimicry, could then interact with and attack central nervous system components. So these two models haven't been really completely defined, and there's evidence supporting a bit of both, but none is conclusively accepted. So how can we target specifically something that we don't even know how it originates? Hence, autologous hematopoietic cell transplantation has been used as initially primarily as a rescue approach in multiple sclerosis, but now is moving to earlier and earlier stages of treatment in the hope to provide a highly effective, durable suppression of disease activity by suppressing inflammation and potentially representing a form of curative treatment as well. However, much of the attraction towards using AHSCT for treatment of MS, as well as other autoimmune diseases, has been driven by the attractive mechanistic notion that the strategy could produce a form of immune resetting. So unlike immune suppressant, immune modulatory treatments, which are given cyclically or constantly to downplay immune system by a form of immune modulation suppression, the strategy of the AHSCT is different, and it involves inducing a hopefully permanent qualitative change of the immune system that has been termed the immune resetting. Now, what is immune resetting, and what evidence do we need to define and support the notion of immune resetting? I put down here a few points. It's not a comprehensive list, but it does include the major components, as we understand, of immune resetting concept. By and large, to obtain immune resetting, you should be able to demonstrate replacement and a renewal of the immune system. So taking away old parts of the immune system and putting in new parts. And this is largely, as we will see, focused on the so-called adaptive immune system, because it's the part of, as compared with the innate immune system, the adaptive immune system is obviously the part, the arm that adapts. And so it evolves during life, and it is possible conceptually to reset it, to reset the clock. For inflammatory autoimmune disease, we want to see a reduction of inflammatory cell or pathways in that will go along, or would sit well with the notions of what are the effector mediators of the inflammatory immune disease. We'd also want to see the regulatory arm potentiated in a way that enables immune tolerance. Lastly, if there are aberrations in inflammatory immune-mediated diseases, we'd want to see them normalized, particularly when we know, such as in the case of MS, that polygenic disease susceptibility has been linked to polymorphisms of immune gene, of a large number of immune genes. So we'll work through these points and review the evidence with some highlights from MS work, scleroderma, and the lupus work. And we'll start with the replacement renewal related work, as I mentioned, focused on adaptive immune system. And starting from the T cell compartment, I want to illustrate how T cell development occurs normally and what markers we can use to define its renewal. So the precursor to T cells in the lymphocyte progenitor cell comes from the hematopoietic stem cells. It evolves through maturation in the thymus, where the T cell antigen receptor, T cell receptors are rearranged. And in doing so, it's important to know that there is a byproduct of this rearrangement of gene loci that is termed the T cell receptor excision circle or track. And this byproduct can be used to identify T cells that have recently emerged from the thymus, so-called recent thymic emigrants. These naive cells that have a naive phenotype, have immune phenotyping, and have high track levels. So, number of groups have looked at these in order to investigate immune receptive. And when I did this work a number of years ago, I collaborated with one of the leading experts in track assays, Danny Jewett, and we looked at patients with MS who underwent transplants performed by Richard Bird, and measured in parallel track levels by PCR, and here are the values, and used phenotype-based enumeration of recent thymic emigrants in patients followed from pre-treatment baseline to 2 years post-transplant. And you can see that following the initial contraction at 6 months, the recent thymic emigrant cells re-expanded and even increased at long-term post-transplant. And this was paralleled by the track analysis, providing the first demonstration of this kind of immune regeneration by thymic population and renewed thymopoiesis. Tobias here also observed a degree of thymic repopulation in patients treated with AHSCT for lupus that he described in his Blood 2009 paper, where they looked at firstly the naive versus memory populations of re-emerging T cells. Here's the percent of memory T cells of OC4 that were clearly ablated or vastly reduced post-transplant that remained low compared to baseline, whereas the population of naive cells expanded, relatively speaking, and within the CD4 T cell compartment, recent thymic emigrants clearly improved, enhanced, increased from the patients before transplants to post-transplant. And the absolute number as well here were calculated and shown to increase. So the mechanism was not specific to MS, it was shared with patients with lupus, and this was the first important convergence of researchers working in this field. And also Dominic Farge and colleagues studied the reconstitution of T cells following transplant in scleroderma patients, where in these early study from her, the important observation that I would like to highlight today was that although variably during immune reconstitution, at longer term, the recovery of track levels was higher in a subgroup of patients who had better clinical responses, group A, than the group B that had about half of the normalized track levels than their fully responding patient counterpart. So you can see here how in at least 3 different diseases that I'm able to highlight today, we have a potentially shared mechanism. Now, moving to the B cell compartment, this had not been investigated in great detail in MS, but Tobias was one of those who actually did study in his lupus work reconstitution of the B cell compartment, where you can see here again that the memory B cell compartment was nearly eradicated post-transplant and persisted, decreased long term. And this was occurred at the expense in terms of repopulation. The repopulation occurred at the expense of memory B cells, because the naive B cell compartment actually repopulated very effectively, resulting in above baseline naive B cell levels. We also did some work on plasmablasts that I really shouldn't take time to discuss here. In order to proceed to the next side of immune repopulation resetting, that is T cell receptor analysis studies. So I've already mentioned that T cell receptors are rearranged prior to kinase selection, but it's important to consider that the newly kinase-produced T cell subset has a highly diverse T cell receptor repertoire, because by and large the rearrangement is stochastic, and the positive selection will enable survival of a large proportion of the possible receptors, hence resulting in great diversity of the receptor repertoire. However, during immune history of a subject, immunization, infections, autoimmune disease, antigen-driven clonal expansion will result in perturbation of the T cell repertoire with oligoclonal T cell expansions. So this will result in a restricted T cell receptor repertoire. And the question